If you want to know how fast a collegiate soccer player actually is, the standard approach is honestly a bit of a nightmare. It involves dragging a few $1,000s worth of highly calibrated laboratory radar equipment out onto a field, setting it up perfectly on a tripod, and running your athletes past it one at a time.
Right. Yeah. It requires just an immense amount of patience and technical expertise, not to mention a budget that most grassroots sports programs simply do not possess.
Exactly. But what if you could replace
Mm.
all of that cumbersome, super expensive lab gear with a single consumer-grade drone? Like literally something you bought off the shelf at a local electronics store. What if you just hovered it over the field and let an algorithm do all the heavy lifting for you?
I mean, it sounds like science fiction for sports coaches, right? But it is a very real, very pressing question in the world of sports biomechanics right now. We are seeing a massive push to democratize elite-level data tracking.
Which is exactly why we are analyzing a really fascinating new study today. The paper is titled, "A Drone-Based Method to Measure Sprint Force Velocity Profiles in 30-Meter Sprint Test, a Pilot Study." It was authored by Fahui, Wang, Christophe, Hautier, and their colleagues, and published in the Journal of Sports Science and Medicine in 2026.
Yeah, it's a great paper.
It really is. So our mission for this deep dive is to evaluate whether a commercially available drone utilizing computer vision can genuinely rival gold standard laboratory radar for tracking athletic performance. And we are looking specifically at the science of sprint force velocity profiling.
Right, and to really grasp the ambition of Wang and his team's experiment, we have to recognize that sprinting is not just a single binary number. Yeah, you do not just cross the finish line, stop a clock, and get labeled fast or slow.
Oh, totally.
The performance landscape is infinitely more complicated because how an athlete accelerates tells us far more than their actual top speed.
Okay, let's unpack this, because before we bring the drone into the picture, the paper revolves entirely around measuring sprint force velocity profiles,
Yeah.
which are often called F-V profiles. So for a listener who, might just watch soccer on the weekends, what exactly is that profile, and why is mapping it out so critical to a coach or a sports scientist?
Right. So think of a force velocity profile as the mechanical DNA of the sprint. So imagine you are an athlete locked into the starting blocks. When you push off, you aren't just moving forward. You are applying massive amounts of horizontal force directly backward into the ground to, overcome your own body weight and inertia.
Right.
So in those first few steps, your force output is at its absolute maximum, but your forward velocity is still quite low.
You were basically grinding to get up to speed.
Exactly that. And as you accelerate and your velocity increases, the amount of time your foot spends on the ground actually decreases. Consequently, the amount of horizontal force you can physically apply to the ground drops.
Okay, I'm with you.
So that inverse relationship, how your force output steadily drops as your velocity peaks, that creates a personalized linear curve. That curve is your force velocity profile.
And the paper points out that this isn't just about shaving like a tenth of a second off a race time to win a medal. This is actually a vital diagnostic tool for injury prevention. They specifically mention hamstring tears. But how does a graph on a computer screen predict a pulled hamstring?
Well, the hamstrings act as the primary engines of horizontal force production, right? Especially during high-speed acceleration. So if an athlete has an imbalanced force velocity profile, say they have great top speed but struggle to produce horizontal force efficiently at certain transitional speeds, their hamstrings are absorbing a tremendous amount of poorly distributed mechanical stress.
Oh, wow. So they're basically a ticking time bomb.
Yeah, they are at a significantly higher risk of a tear. By mapping this profile accurately, a coach can prescribe highly specific strength training to fix that mechanical imbalance before the hamstring ever snaps.
That makes perfect sense. You map the mechanics to protect the engine. But trying to get that continuous, highly accurate force data seems incredibly frustrating given the tools most teams currently rely on, right? The researchers outline the limitations of traditional tech, and it paints a pretty grim picture for your average high school or collegiate program.
Oh, definitely.
Like if you try to build a continuous force velocity profile using traditional photocells, those little laser timing gates you set up along a track, it's basically like trying to understand an entire 100-meter dash by looking at just 3 Polaroids taken at the 10, 20, and 30-meter marks.
Yeah.
You get the split times, but you are completely blind to everything happening in the physical spaces between the cameras.
Yeah, you are left with sparse, highly segmented data. You simply cannot build a smooth, continuous mathematical curve out of 3 data points.
Right. And then you have GPS vests, which, players seem to wear constantly now, even during practice. But relying on a GPS unit for millisecond by millisecond acceleration data feels like trying to watch a 4K video on a dial-up internet connection.
That is a great way to put it.
Yeah, the satellite sampling frequency is generally too low, maybe 10 or 15 hertz, so the data just buffers and stutters. And if a cloud cover rolls in or, a stadium roof blocks the signal, your data is totally compromised.
If we connect this to the bigger picture, this is exactly what forces elite programs to rely on the undisputed gold standard of sprint tracking, which is laboratory radar systems. The researchers in this study specifically used the Stalker ATS-2 radar to validate their drone. Radar bounces radio waves off the runner hundreds of times a second, delivering just flawless continuous velocity data.
But a lab-grade radar is essentially a highly accurate single-lane toll booth. It operates on a very narrow, direct line of sight. You have to set it up perfectly on a tripod directly behind the runner, and it only tracks one athlete at a time.
Right.
If you're managing a squad of 30 soccer players, testing them one by one, calibrating the radar every single time, that is an absolute logistical nightmare.
It is. The overarching bottleneck here is financial and practical access. Radar systems cost thousands of dollars. GPS requires ongoing software subscriptions and physical hardware for every single player on the pitch. These tools place a crushing financial burden on grassroots clubs and amateur teams.
Which brings us to the drone.
Exactly. The drone vision system proposed by Wang and his colleagues represents a potential democratizing breakthrough. Theoretically, a single drone hovering 50 feet in the air could record an entire field of athletes sprinting simultaneously, extracting lab-grade biomechanical data for a fraction of the cost, without anyone wearing a single piece of equipment.
Okay, but if radar is too expensive and GPS is too slow, how does a $1,000 consumer drone not suffer from those exact same accuracy issues? Let's look at how they actually designed this eye-in-the-sky experiment.
Let's do it.
So they brought in 17 male collegiate soccer players and had them run 30-meter maximal sprints. And the hardware setup is surprisingly accessible. They took a DJI Air 3's drone and hovered it exactly 32 meters above the center of the track. Then they recorded the sprints in 4K resolution at 60 frames per second.
Right, and 60 Hz provides a sufficiently dense temporal data set. But raw 4K video from a drone is essentially useless on its own. The heavy lifting happens entirely in the computer vision pipeline. First, they have to stabilize the footage digitally, because even if a sophisticated drone is hovering perfectly still, it is constantly making micro-adjustments against wind currents. It wobbles.
Yeah, and if the drone drops even a few inches in altitude during a gusted wind, the scale of the pixels on the ground changes, right? A player would suddenly look larger, which a dumb computer program might interpret as the player suddenly accelerating, and that would completely ruin the speed calculation.
Exactly. They mitigated that by using algorithms to lock on to the stationary white lines of the soccer field. By digitally anchoring the video to those static pitch lines, they completely neutralized any camera shake or altitude variations. But the true engine of this methodology is the object detection model, which is a system called YOLO-8s.
Oh, YOLO. That stands for You Only Look Once, right? It's a highly popular single-stage object detection model used in artificial intelligence.
Yeah, that's the one. The researchers fed this neural network over 3,000 annotated images to train it to recognize the shape of a human athlete specifically from a bird's eye view.
Okay.
The algorithm's job is to draw what's called a bounding box, which is just a digital 2D rectangle around the outermost pixels of the player, and then track the geometric center of that rectangle frame by frame as the player moves.
See, I am looking at this methodology, and I have to push back on the physics here a little bit. I understand how an AI can track a colorful box moving across a computer monitor. But wait, a bounding box is literally just a 2D rectangle drawn around shifting pixels. A video file has no concept of physical depth.
Right, it's flat.
So how does tracking a floating rectangle on a flat screen give us precise real-world distance and velocity measurements in meters and seconds?
Well, you are highlighting the core challenge of computer vision right there. To bridge that gap, the researchers utilized a perspective transformation algorithm. They mathematically mapped the 2D pixel coordinates from the video onto a 3D real-world coordinate system. By knowing the exact physical distance between the white lines on the field, the algorithm creates a localized grid. It calculates precisely how many real-world centimeters each individual pixel represents from that specific hovering altitude.
Okay, so the field lines give the camera a physical anchor. But even with that grid, tracking a bounding box from a drone surely introduces massive high-frequency noise, right? I mean, the human body isn't a rigid block of wood. As a player runs, their arms pump outward, their legs extend.
Oh, absolutely.
So that bounding box is going to constantly jiggle and expand and contract frame by frame to fit those moving limbs. If you calculate speed by measuring the center of that jiggling box from one frame to the exact next frame a 60th of a second later, your data is going to look like chaotic, unusable static.
The raw frame-to-frame data is indeed incredibly noisy. To solve this, the researchers implemented a specialized smoothing technique. They adjusted the time increments using a 0.5-second sliding window.
Walk me through how a sliding window actually smooths out the jiggling pixels. Like, how does that work in practice?
Sure. Imagine you are driving a car over a rough gravel road. If you put tiny skateboard wheels on the car, you're going to feel every single pebble, right? The ride is violent and erratic. That represents looking at the data frame to frame. Now, imagine replacing those tiny wheels with massive, heavy monster truck tires. The large tires roll right over the gravel, absorbing the micro bumps and creating a smooth, continuous trajectory. The 0.5-second sliding window acts like that massive tire. Instead of calculating velocity between frame 1 and frame 2, the algorithm looks at the athlete's position 15 frames ahead and 15 frames behind.
Oh, because at 60 frames per second, 15 frames is exactly a quarter of a second in either direction.
Correct. By computing the average velocity over that larger half-second window, the algorithm effectively irons out the high-frequency pixel noise caused by pumping arms and legs. Once they extracted that smooth position time data along the straight line of the sprint, they needed to convert it into force. To do this, they applied a well-established exponential mathematical model created by Morin and colleagues in 2019.
Wait, how does knowing a player's position tell us the mechanical force their hamstrings are generating? What is the actual physics equation happening in the Morin model?
Well, it relies on fundamental Newtonian physics. If you know an athlete's exact position at specific time intervals, you can calculate their velocity, which is just how fast their position is changing. If you track how their velocity changes over time, you have their acceleration.
Basic kinematics, right.
Exactly. Finally, Newton's second law states that force equals mass times acceleration. By plugging the athlete's body mass and a standardized estimate of aerodynamic friction into Morin's exponential curve, the algorithm mathematically extrapolates continuous horizontal force from nothing more than the drone's position data.
The theoretical math is really elegant, but, a pilot study has to prove it works in the mud and the grass. The researchers ran the soccer players, tracked them with the consumer drone and the $2,000 lab radar simultaneously, and compared the results. And for the maximum speed phase of the sprint, the results are genuinely startling. The drone actually holds its own.
It really does. When evaluating a new measurement tool in sports science, the first hurdle is test-retest reliability. If a player runs with the exact same mechanics twice, does the drone output the exact same numbers both times? We measure this using an interclass correlation coefficient, or ICC. An ICC score closer to 1.0 indicates perfect reliability.
And the drone hit scores between 0.59 and 0.95 across various metrics, showing moderate to excellent reliability. But it really dominated in specific speed metrics. Maximal velocity, known as Vmax, theoretical maximal velocity, V0, and late phase acceleration, which are the split times from the 5-meter mark out to the 30-meter mark. Here's where it gets really interesting, though.
Oh, yeah.
It's just amazing that a commercially available drone can match a laboratory-grade radar once the athlete hits top speed.
Well, we have to be very rigorous about what it means when we say the drone matches the radar. The researchers utilized two distinct statistical methods to validate the drone: a linear mixed model, or LMM, and a Bland-Altman analysis.
See, I am looking at this data, and I don't get why they ran two completely separate statistical tests to prove the exact same thing. Doesn't the linear mixed model already tell us if the drone is accurate?
They run two tests because they're investigating two entirely different types of error. The linear mixed model checks for systematic bias. It asks the question, is the drone consistently measuring slightly higher or slightly lower than the radar across all trials? And the LMM actually revealed a statistically significant bias for maximal velocity. The drone consistently estimated Vmax slightly differently than the radar. This could be due to minute discrepancies in the drone's actual frame rate versus the radar's radio frequency sampling.
Oh, interesting. So statistically speaking, the drone was technically wrong.
Statistically significant, yes, but practically meaningful, no. That is where the Bland-Altman analysis steps in to save the day. A bland Altman plot visualizes the absolute magnitude of that error. It plots the differences between the two devices against their averages, creating what we call limits of agreement. It asks, even if this systematic bias exists, is the error margin large enough to actually mislead a coach?
I see. Because if the radar says a player's top speed is 30,000 kilometers an hour and the drone consistently reads 30.001 kilometers an hour, the linear mixed model flags that as a statistically significant, predictable bias. It happens every single time. But as a coach standing on the touchline, I do not care about a thousandth of a kilometer an hour. It doesn't change my training program at all.
Precisely. The bland Altman analysis proved that while the drone had a systematic bias, the absolute magnitude of that error from maximum velocity was entirely negligible, under 1.12%. The limits of agreement were incredibly narrow. So for evaluating a player's absolute top speed, this off-the-shelf drone is highly valid and practically useful.
But wait, the entire foundation of a sprint force-velocity profile relies heavily on the explosive mechanics of the first few milliseconds, right? Athletes don't just magically spawn on the track moving 30 kilometers an hour. What happens to the drone's accuracy when the athlete is dead still and aggressively pushes off the block?
Well, that is where the algorithm completely falls apart. The statistical validation just fractures.
Yeah, the paper shows that for the early acceleration metrics, the drone's reliability plummeted and the bland Altman limits of agreement widened to over 10% error. We are talking about the critical measurements here. The theoretical maximal horizontal force, or F0, the max acceleration Amax, and the overall downward slope of the force-velocity relationship.
It's a huge problem.
It is. Why does a drone recording at 4K resolution and 60 frames per second work flawlessly when a player is running fast, but fail miserably at measuring how they started running fast? The camera hasn't changed, the sliding window hasn't changed. What physical mechanism breaks in those first 5 meters?
The failure comes down to biomechanics, specifically a phenomenon known as the postural shift. Picture an athlete at the start line. They're in a deep horizontal crouch, leaning heavily forward to push into the ground. As they explode forward and accelerate over the first few strides, they rapidly unfold. They transition from that deep forward lean into a tall, upright, vertical sprinting posture.
Right, so their physical shape in the camera's lens is morphing drastically.
Exactly. And remember how the YOLO algorithm tracks the athlete. It draws a 2D bounding box around their outermost pixels and tracks the exact geometric center of that rectangle. When the runner is crouched, the geometric center of the box aligns reasonably well with the athlete's biological center of mass, their hips and chest. But as the runner stands upright, the digital box has to grow taller to encompass their head and feet.
And as the box grows taller, the geometric center of the rectangle is mathematically pulled downward and backward away from their actual chest. Oh, that's wild. It's like trying to measure the exact speed of a moving car by tracking a balloon tied to its antenna that's violently blowing back in the wind. The reference point keeps shifting. The car is accelerating smoothly forward, but your tracking reference point is shifting backward while the object is moving forward.
This raises an important question, right? Because that analogy perfectly isolates the mechanical failure. How much error does a shifting reference point actually inject into the math? The authors cite a vital study by a researcher named Bizodis and his colleagues, which demonstrated that if a tracking point shifts backward by just 0.25 meters relative to the center of mass during the first critical second of a sprint, it causes massive, catastrophic discrepancies in the velocity calculations.
Because the sliding window smoothing technique we talked about earlier, that can't fix a tracking point that is fundamentally migrating across the player's body.
Not at all. Furthermore, the drone suffers from 2D perspective projection errors. The drone is hovering over the exact middle of the 30-meter track. When the athlete is at the start line, 15 meters away from the camera's direct optical center, the viewing angle is severely skewed.
Oh, right. Think of a subtle fisheye effect.
Exactly. The 3D human body is being flattened into a 2D image from an angled perspective. As the athlete accelerates toward the center of the camera lens, that perspective distortion rapidly changes. This complex cocktail of an unfolding human posture and changing camera angles injects massive high-frequency noise right at the exact millisecond the athlete is producing their highest horizontal force.
Whereas the laboratory radar does not suffer from this blind spot because the radar wave is physically locked onto a single reflective point on the runner's lower back. It doesn't care if the runner is leaning, standing, or doing a cartwheel. It measures the physical distance to that one specific anchor point.
That's right. The bounding box approach simply lacks the sophistication to handle the extreme morphological instability of a human body aggressively unfolding from a crouch.
So, distilling all of this down, what is the ultimate takeaway for you, the listener? Whether you are a sports scientist, a collegiate coach, or simply fascinated by the intersection of AI and athletics, drones are clearly a highly practical, cost-effective tool for group-level monitoring of maximum velocity. If you want to efficiently capture the top speed of an entire soccer roster in an afternoon, this methodology is fantastic.
However, coaches and researchers must exercise extreme caution before relying on bounding box drone technology for individual monitoring of early acceleration. If you are designing rehabilitation programs or calculating hamstring injury risk based on a player's initial horizontal force output, the current YOLO bounding box algorithm is simply too noisy and unreliable.
The blind spot is massive, but, the researchers explicitly point to the future in their limitations section. To fix this postural shift error, the technology must evolve past bounding boxes. The next leap is pose estimation. Instead of drawing a dumb rectangle around the player, advanced AI will track specific skeletal anatomical landmarks like the exact pivot point of the hip joint, maintaining a lock on the center of mass, regardless of whether the athlete is crouching or standing.
Right, and once pose estimation becomes computationally light enough to run reliably on these drone videos, that 10% error margin at the start line will likely just vanish.
It is a brilliant pilot study that clearly outlines the bleeding edge of sports technology. If you want to dig into the specific mathematical formulas, study the perspective transformation matrices, or examine the detailed Bland-Altman scatterplots for yourself, I strongly encourage you to read the full article by Fahui Wang and his team in the Journal of Sports Science and Medicine. Also, please make sure you follow our channel and turn on notifications so you never miss our deep dives into scientifically rigorous, cutting-edge research.
The methodologies will only get more precise from here for sure.
And on that note, I want to leave you with a final puzzle to chew on, pulling directly from the horizon of this research. This entire study focused on athletes running in a perfect 30-meter straight line. But team sports like soccer, rugby, and basketball are beautifully chaotic. They are non-linear. What happens when we attempt to apply this drone technology to track curvilinear sprints or complex, rapid change of direction movements across a crowded field? How aggressively will those 2D perspective projection errors multiply when a player is weaving, leaning heavily into a curve, or cutting sharply against a defender? Could a multi-drone stereoscopic setup using 2 or 3 drones to triangulate a player's hips from multiple angles simultaneously be the ultimate key to unlocking real-time, flawless biomechanical data in the middle of a live match? Keep your eyes on the sky.